all good things must come to an end, and so does this conference. So I'd like to welcome you to the final talk today. We have Zdeslav Vojković with a really interesting, to me at least, topic, ZeroMQ. So please welcome Zdeslav.
Hi everyone, thanks for staying this long. My name is Zdeslav Vojković. I'm a freelance software developer, and I will tell you a couple of things about using ZeroMQ to build high-performing distributed applications. Modern applications are typically distributed in the sense that they consist of components which are either logically or quite often physically separated and which exchange the state by the messages. Sometimes it happens that they don't have the same performance or timing requirements, like in this example here, where you can see the first, this is some imaginary image processing application, where there is a web application where users can submit their tasks. It is a simple HTTP request, and the web frontend stores the task information into the message queue, and then can continue serving other users. Then there is some kind of typically more than one, image processing workers, which pick up tasks from message queues and process it for some minutes, hours, whatever, and when they're done, they store the completion event with all the required information back to the message queue. Then there is also the third component, which is some kind of notifier, which picks up these completion events from the message queue and notifies the user by sending them email or whatever. For such systems, we typically use message queues because they are really an excellent tools for such decoupling of the applications. However, they have their own problems. First of all, they force you to have some kind of centralized architecture when there is this single point of failure, which can be then overcome by deploying your message queues in a cluster configurations, which brings its own problems and so on. However, there is a lot of great tools in this area. For example, there is ActiveMQ, there is Apache Cupid, there is MSMQ, which is not that great really because it lacks a lot of things. And my personal favorite, which is RabbitMQ. Quite often ZeroMQ is put in the same box with these tools, but that's actually a lie, because ZeroMQ is not really a message queuing system. ZeroMQ, the name is a bit misleading. ZeroMQ in the name means no MQ. It doesn't have a centralized broker. Instead, it's a networking library for writing asynchronous messaging applications. It doesn't really force you to use some predefined architecture. It's routing and topology aware, which means that out of the box it comes with support for different configuration, different topologies. It's completely brokerless, which means components are typically connected in a peer-to-peer fashion, although you can build your own custom brokers with it depending on your needs. It has a very high performance, typically orders of magnitude better than standard message queues, but it's not really a fair comparison because they are not the same things. It provides multiple transports out of the box, depending on your needs. It runs both on Windows and various flavors of Linux, and it provides also libraries for more than 30 languages, C++, Java, Python, Ruby, Node.js, whatever. You name it, everything is there except Go. That's not it. And last but not least, it's LGPL licensed. Okay, let's switch to design and implementation of ZeroMQ. As I already said, there is no broker. This helps reduce the chatter between components, but it also affects how you lay out your system. Typically, it makes you lay out things more in a pipeline-oriented fashion, which can help you with performance, but of course, it's not always the proper solution for every problem, so you should take care about it. It provides, ZeroMQ provides its own sockets, which are way better than the conventional sockets for the following reasons. TCP socket is actually an abstraction over a reliable stream. On the other hand, UDP is an abstraction over unreliable datagram. What you really want is a reliable datagram. That's what you want in messaging applications. And you don't have that with typical, with conventional sockets. Besides that, they are connected typically one-to-one, so for 3 clients you have 3 sockets, you need to do it like that. You need to start the server before the client, otherwise you cannot obtain the connection. they are typically synchronous, and if you want to use them in an asynchronous way, it gets even more complicated and so on. On the other hand, ZeroMQ sockets are different things. They are abstractions over in-memory message queues, which are then communicating asynchronously through a background thread. So when you write something to one socket, it gets stored into an in-memory queue of messages, so it's not really a stream, it's really a list of messages. Then you have this background thread, which takes the messages from one queue, writes them to the other side, and then on the other side, other socket pulls it from the message queue. This really simplifies the architecture of your solution. And the other nice thing is that you can connect one socket to 3 different endpoints and use only that socket to communicate with them. So you don't have to have 3 sockets for 3 clients, you have one socket. The messages are also very important in the ZeroMQ library as an entity. As I already said, they are asynchronous, they are atomic, which means that either you get the whole message on the other side or you get nothing. You don't have to do parsing, you don't have to invent your own protocol with length prefixes, terminators, or both, and so on. Also, they support multi-part messages, which is a very nice thing to provide some additional metadata with your message and send it to the other side. ZeroMQ internally uses, for example, such pre-appended frames for routing, because it enters sender ID, sender address before the payload, and then it can route it back when there's an answer for such a message. It provides very low latency in range of TCP sockets, maybe slightly worse, and very high throughput, sometimes even better throughput than raw TCP, because they use quite smart way of batching messages and sending them as one message. So you can have a really high throughput. Messages themselves are zero-copy messages, which means that they are never copied. When you create a message object on the stack, if a message is short, then the whole message is really kept on the stack. There is no heap allocation, which is typically quite slow. If you have a large message, it is allocated on the heap, but then it's reference counted. And if you have some kind of in-process communication, or you copy it from different queues, you copy the message object, but it's reference count. You don't really copy the payload. So you save a lot of time on copying stuff, which can reduce your time to the execution. Besides that, there are other socket options which you can use to improve the performance of your solution. On the project which I currently work on, we were using RabbitMQ for some other things, because we need really durable queue, so we use RabbitMQ for that, not ZeroMQ, which doesn't fit it. However, we also implemented some kind of distributed loggers, where multiple services log to the same logging service. And since we already have RabbitMQ, we put all that to the RabbitMQ. And we were able to get 4,000 to 5,000 messages per second, which is great for a message queue. However, we decided to reduce that load on RabbitMQ, and we changed logging to use ZeroMQ, and we get up to 250,000 messages per second. It's a huge number. So, and we use less CPU besides. API of ZeroMQ revolves around 3 main objects. There is one global context, which stores some common data for one application. There are sockets and messages. Typical flow is that you create this global context object, and then you use that to create sockets, which you can bind or connect depending which side of the equation you are, and then you use it to send or receive messages. Here's an example of Python implementation of a simple publisher and subscriber. So as you can see, we create the context. This number 1 means how many background IO threads will there be. And for most applications, you need only one. These 250,000 messages is achieved with only one background thread. Then you create a socket. In this case, you have to specify type of socket because it provides different types of sockets for different scenarios. You create a socket, you bind it, and you send some data. Client is equally simple. You create a context, create subscriber socket, in this case, connect it to the same endpoint, and then you receive the data. There are a couple of interesting things. First of all, you can connect one client to multiple servers, and you will get all these events from different publishers through the same socket. It simplifies your coding quite a lot. Other thing is that you have this socket receive, which is what we call, unless you set the timeout, but sometimes you really want to listen to multiple sockets. In that case, there is a poller object, which you can provide with a list of sockets, and then you get notified when there is some data to be read from any of them. So you can also do that easily. What's not there is, like with conventional sockets, there is no serialization. Although some libraries, you need to use your own protocol buffers, message pack, whatever. But some clients provide their own serialization, like for example, Python library by ZeroMQ provides way to serialize your objects as JSON or pickled object or whatever. There is no compression, there is no security because actually there is no security. Although in last version they implemented some kind of encryption, but it's not really battle tested, so I would not suggest anyone to use it because it's proved that it really works in real life scenarios. There are a lot of transports which are supported actually for out of the box, depending on what kind of application you need. So if you need to talk across machine boundaries, you of course use TCP. If you want to talk between processes in the same box, you can use IPC. Unless you use Windows, then you're out of luck. It doesn't work on Windows. You can use in-process transport for communication between threads in the same process. This uses some in-memory buffers in the application, and it's very, very fast. And if you want to use publish-subscribe configuration, you can use PGM. PGM is a less known transport for reliable multicast. It can reduce your overall resource usage compared to when you use TCP sockets to distribute all these events. So here's an example. Also, these transports are, except improv transport, are typically transparent to your application. So here we have an example of changing the previous publisher-subscriber example from TCP to IPC as they, let's say, they run on the same machine. You just need to change the endpoint. That's all. The rest of the code remains the same. If you need to scale it out of the box and you have such an infrastructure, you could change, replace IPC with PGM, and then it would use PGM to communicate between different nodes. Other important thing are communication patterns. As I already said, ZeroMQ is topology aware, which means that it helps, it provides some solution already out of the box for typical communication scenarios. First one is typical publish-subscribe scenario. You have one publisher, multiple subscribers. For that, you have pub and sub sockets. We have seen that earlier in this code sample. Typically, you connect subscribers to publishers, and you can easily get events. Nice thing is that you can, already said, connect one subscriber to multiple publishers. It will work without separate connections. Other thing is that you can subscribe not to all messages, but just to some of the topics. Okay, I have the older version of my presentation, but never mind, they're similar. So you can subscribe only to some of the topics which you are interested in and not get all of them. Then the problem with this solution is that what happens when you need to add additional publishers. Then you need to go through all the subscribers and reconnect them to the new publisher. This obviously doesn't scale. So for that you can use these XSub, XPub sockets, which are similar to normal pub-sub sockets, but they also transfer the subscription messages from here up to here. This way you can create simpler deployment environment for you. You connect all the publishers to the XSub, all the subscribers to the XPub, and they, when you have a new publisher, you just connect it here to the XSub, and everybody will get the new messages. The proxy part is just a simple function which reads messages from here and writes them here, and also the same in this direction. It is actually such a common thing in ZeroMQ that there is a function which takes two sockets and does all this message shuffling from one to the other side. Other pattern is client server, which is more or less akin to the RPC communication. You have rec-rep request response sockets for that. You can connect one request to multiple response sockets, which are real servers, and then all your calls are distributed in a round-robin fashion around them. The problem with this is that they work in lockstep. When you call send on a rec, you need to call receive on rep, and it will block until there is a reply. You cannot call another send because before your receive is finished. The problem is what happens when your server crashes. There is never answer for the receive, so your application is blocked. That's obviously not good. So you can use this router and dealer sockets, which provide some nice features, more or less asynchronous client-server communication, but also some nice routing features. So when there's a reply from the server, router knows to which client to return the answer. They also provide some other nice things which allow you to have some really sweet topologies and do some really nice things. Next pattern is the parallel pipeline, when you want to distribute your work between multiple workers. For this, we use push and pull sockets. Typically, you have one producer. It uses push socket to push tasks to multiple workers in a round-robin fashion. Then workers use their pull sockets to get that work. They process it. They write the results through push socket back to the pull. This requires quite a small amount of code to do it in such a manner, and you can really distribute it like this with little effort on coding side. The last pattern is thread signaling or thread communication. For this, there are pair sockets, which are actually very similar to conventional sockets in a way that they are one-to-one. They are not many-to-many, and they. In this case, you need to do the bind before the connect, and also if connection breaks, they will not reconnect automatically. I didn't mention that before, but ZeroMQ sockets internally take care of reconnecting in case of disconnect and reconnect, so you don't have to worry about it. You don't have to write your own code. For that, it will be automatically connected. This is also what allows ZeroMQ to start the client before the server. It will connect when the server is available. Okay, actually I'm quite fine with time. This gives me a chance to show you a couple of designs or topologies which you can implement with ZeroMQ sockets. The first example, this picture is taken from excellent documentation from the ZeroMQ website. There's a whole book about different solutions, and they show you multiple designs which can be achieved with these couple of sockets which we just mentioned. Let's see some of these examples. Here, this is the one which I mentioned previously with distributed logger, which we implemented on this current project. It's actually a simple thing. You have multiple services doing whatever, and they're sending their log messages to the logging service, which is subscribed to all of them, and it just picks them up and writes them to some persistent storage, whether it's a file database, it's really irrelevant. We implemented it completely in, I don't know, it was a couple of minutes, literally. It worked out of the box. I was extremely surprised that it went so flawless. Next thing is better known project than the previous one. It's Mongrel 2. It's a web server which, I don't know, maybe some of you have used. I haven't personally, I don't know. But it is designed in a way that there is a core which has push and sub sockets, and there are multiple handlers which have pull and pub sockets on their side. They can be implemented in any language which is supported by ZeroMQ, and it works in following fashion. When there is an HTTP request, the core part, I'm not sure what's the official name for the core part, takes this request and it sends it to the handlers through this push socket. As we said before, a push socket delivers them in a round-robin manner, so the next available handler picks them up through the pull socket. Then it starts to process this task, whatever it is, and when it's done, it fires an event through its publisher socket, which is picked up on this subscription socket and returned to the client. The reason why the numbers are not continuous, 1, 2, 7, 8, is that during this processing of the handler, there can be another request, 3, 4, which will end up here and be processed here. So it really depends. Another example is actually quite the opposite thing. It's some kind of chat server. You have a client which sends a message to the server through push socket to the pull socket, and then the server simply reads it from the pull socket and writes it to the pub, to which all the clients are connected, and they all get these messages delivered to each instance of the client. And the last thing which I would like to show you, so you're only a couple of seconds late with the schedule, is extension of pipeline which is controlled by the consumer. The pipeline I can show you before this push configuration, and that part is the same. You have producer with push, multiple workers with pull, and consumer with pulling from the workers. However, the difference is that consumer has a pub socket to which all other components are connected. Sub, they're connected to this one. So consumer can handle all these results of the workers, but depending on some configuration, it can control the throughput or throttle the throughput of the whole system by sending stop, pause, spawn another worker or similar commands to the producer, to the workers, or some controller outside of it. So the point is that with only a handful of socket types, you can create a lot of different solutions depending on your real needs, which you cannot really do in a similar manner or with same performance with classical MQ systems, which have, of course, other additional benefits. So this more or less covers what I wanted to show you in such a short time frame. Thanks for listening. There is great documentation on this address here, and of course you can ask me any questions you want.
Hi. So, do you have any experience with situations where none of the contributing hosts know anything about any of the others? So, cloud providers like Heroku or Amazon, where you don't want a central location. Like, is there a method of discovery of the types of?
Yeah, that's the biggest problem. At least in my experience, discovery is the problem which is not solved for you. You need either to have pre-configured list of the endpoints, which is not really scalable. You need to use some other service like Zookeeper. I didn't try it, but I heard that the combination of ZeroMQ with Zookeeper works flawlessly, whatever that might mean, but people say so, I don't know. So that's one possible solution, and also on this guide, you also, the authors of the ZeroMQ show you a lot of buttons which solve exactly this problem. For example, they have some solutions for discovery problems where you have centralized directory, so you can use that. Or they also have implementation of some kind of beacons, for example. So you even don't have a directory with pre-configured things, but as any new instance comes around, others can pick it up. So you can choose more dynamic or less dynamic configuration, and it works. I haven't tried it personally, but it seems to work. I don't know.
Hey, while I do appreciate the bare boneness of ZeroMQ, I'm interested if there are any like standardized containers in which you place your messages. For instance, you know, like saying where you have like HTTP status header or something. Is there like a standard that you need to roll your own every time? So I don't think like protocol buffers. Of course, you can do that. But is there a standardized like method of transport for that?
I'm not sure if I got you correctly, but there is no support of any kind for serialization. So you cannot do it out of the box like with the conventional sockets. You need to use protocol buffers. If you think of storage for this, then no, this is completely in memory. This is not persistent. This is why it's not fair to compare classical MQs with ZeroMQ.
No, I'm saying that if I have two different applications that need to talk to each other, so I don't reinvent the wheel of the message was processed okay, there was an error, and so on.
But no, it's interesting for me also.
So very simple. Try to emulate asynchronous HTTP push. So you have headers, you have status code. Is there some like standardized?
No, and additionally ZeroMQ is not really transport neutral, so you cannot that easily connect it to the normal sockets and talk with HTTP clients, for example. At least before version 4, now they have some socket options with, when you get the raw server, and you can do it, but it's not the use case which is out of the box. So it's meant more to be used behind some boundary. Like in the example of Mongrel, you have the Mongrel getting the request, but what is sent to the handlers is not the plain request, it's some kind of structure which is sent there. So yeah, you don't have a solution for it integrating with external clients out of the box.
Okay, there is no more time for questions, so thank you very much.